A silence unlike any other blankets the farthest reaches of West Antarctica. There are no forests bending in the wind, no rivers carving valleys, and no cities humming with life. Endless fields of ice stretch beyond every horizon, reflecting sunlight with such brilliance that they appear almost untouchable. For generations, this frozen frontier seemed eternal, a place where time itself moved more slowly than anywhere else on Earth. Yet beneath that dazzling surface, one of the most consequential transformations of the modern era has been quietly unfolding, almost entirely hidden from human sight. Far from the world's crowded coastlines, a river of ice roughly the size of the American state of Florida, covering nearly 74,000 square miles, or approximately 192,000 square kilometers, has become the focus of one of the largest scientific efforts ever mounted in Antarctica. Aircraft equipped with ice-penetrating radar have crossed its windswept surface countless times. Satellites have measured changes so subtle they amount to only a few inches, or several centimeters each year. Autonomous underwater vehicles have ventured beneath floating ice shelves where sunlight has never reached. Teams of scientists have endured months of darkness, temperatures far below freezing, and some of the harshest weather on the planet for a single purpose: understanding the future of Thwaites Glacier. Its popular nickname, the Doomsday Glacier, has spread across headlines around the world, conjuring images of an unstoppable catastrophe waiting to unfold. The truth emerging from the latest scientific research is both more measured and, in many ways, even more remarkable. Rather than pointing toward an immediate collapse, the newest evidence reveals a glacier that has entered a sustained period of retreat, driven by powerful natural processes that are now being observed with unprecedented clarity. Research published throughout 2026 has strengthened that conclusion, offering the clearest picture yet of why Thwaites continues to lose ice and why scientists consider its future one of the defining questions of modern climate science. Understanding the significance of these discoveries begins with recognizing that glaciers are not frozen statues. They are immense rivers of ice that flow continuously under their own weight. Although the movement is almost imperceptible to the human eye, the ice within Thwaites has been traveling toward the sea for thousands of years. Snowfall across the Antarctic interior slowly compresses into dense glacial ice, adding layer upon layer until gravity begins pulling the enormous mass outward. In many places, the glacier advances only a few feet or several meters each day, yet over centuries those tiny movements transport staggering quantities of ice toward the coast. For much of its history, this outward flow remained balanced. Fresh snowfall replenished the ice being lost at the edges, allowing the glacier to maintain an approximate equilibrium. Scientists now believe that balance has been steadily eroding, not because of a single dramatic event, but through the combined influence of warming oceans, changing ice dynamics, and the unique shape of the landscape hidden beneath the glacier itself. Unlike mountain glaciers that rest securely upon elevated terrain, much of Thwaites occupies a basin where the underlying bedrock lies hundreds to thousands of feet below sea level. This unusual arrangement makes the glacier exceptionally vulnerable to changes occurring at its base. Where the ice finally becomes buoyant and begins floating upon the ocean lies a critical boundary known as the grounding line. It is here that one of Antarctica's most important battles is taking place. The grounding line marks the transition between ice firmly anchored to the continent and the floating ice shelf extending over the ocean. As long as that boundary remains relatively stable, the glacier retains much of its resistance to rapid change. Once the grounding line retreats inland, however, the glacier may begin exposing progressively thicker ice to seawater. Thicker ice flows more rapidly under gravity, delivering still greater volumes of ice toward the coast. Scientists refer to this self-reinforcing process as marine ice sheet instability, a mechanism that has occupied glaciologists for decades because of its potential to sustain retreat long after the initial trigger has occurred. For years, researchers debated whether Thwaites had entered this state or whether the observed changes represented temporary fluctuations. Modern satellites, combined with increasingly sophisticated numerical models, have finally begun providing convincing answers. One of the most significant scientific advances published during 2026 appeared in Geophysical Research Letters. Researchers led by D. N. Goldberg, Mathieu Morligam, and their colleagues compared the glacier's latest satellite observations against advanced simulations projecting its future behavior. Rather than asking what the glacier might do, they examined whether its present-day behavior already resembled scenarios that earlier models had forecast. The comparison revealed an unmistakable pattern. Measurements of grounding line retreat, surface thinning, and accelerating ice flow closely matched simulations associated with substantial ice loss over approximately the next 50 years. Instead of finding evidence that the glacier was slowing or regaining stability, researchers found that ongoing observations aligned with scenarios once regarded among the more severe possibilities considered by earlier modeling efforts. Perhaps the most important conclusion was not dramatic but profoundly significant. The glacier is behaving consistently with sustained retreat rather than temporary fluctuation. That distinction reshapes the scientific discussion. Temporary fluctuations often reverse as environmental conditions change. Sustained retreat indicates that the glacier's dynamics have shifted into a new state, where continued ice loss becomes increasingly likely unless fundamental driving forces also change. Confidence in that conclusion stems from the remarkable convergence of independent evidence. Satellites measure changes directly from orbit using radar, laser altimeters, and other remote sensing technologies. Numerical models rely instead upon the physical laws governing ice flow, gravity, temperature, and ocean interactions. Each method contains its own assumptions and uncertainties. When both independently point toward the same conclusion, scientists gain far greater confidence that they are observing a genuine physical transformation rather than a measurement artifact. Yet satellites reveal only part of the picture. The true engine driving many of the glacier's changes lies hidden hundreds of feet below floating ice shelves, where relatively warm seawater circulates through deep submarine cavities. Despite Antarctica's frigid reputation, parts of the Southern Ocean contain a water mass known as circumpolar deep water. Although only several degrees above the freezing point of seawater, it carries enough heat to melt glacier ice efficiently whenever ocean currents transport it beneath floating shelves. This process differs dramatically from the surface melting familiar in mountain environments. Instead of sunlight melting ice from above, the glacier is gradually eroded from below. Warm seawater enters hidden channels beneath the floating shelf, transfers heat into the ice, and slowly carves away its underside. Over time, the shelf becomes thinner, weaker, and less capable of resisting the immense pressure exerted by the inland glacier. That floating extension serves a purpose far greater than simply occupying space over the ocean. It functions as a natural brace. By remaining attached to embayments, islands, and underwater ridges, the shelf exerts resistance against the glacier behind it, slowing its movement toward the sea. Glaciologists describe this restraining influence as buttressing. Reduce that buttressing, and the glacier responds. Ice upstream begins flowing more rapidly. More ice reaches the coastline. The grounding line may retreat farther inland. Additional retreat exposes thicker ice resting upon deeper bedrock, reinforcing the very cycle scientists have long feared. Research emerging during 2026 from the International Thwaites Glacier collaboration has added remarkable detail to this process. Drawing upon years of coordinated field campaigns involving scientists from multiple nations, these studies consistently identify warm circumpolar deep water as the dominant source of melting beneath the glacier's floating ice shelves. They also report continued grounding line retreat, ongoing thinning, increasingly complex ocean circulation beneath the ice, and growing structural weaknesses within the remaining eastern ice shelf. Those fractures have attracted particular attention because they reveal that the shelf is responding to years of internal stress as well as continued melting from below. Long crevasses now extend across sections of the floating platform, indicating that its structural integrity has weakened considerably. Scientists emphasize that this should not be interpreted as evidence of an imminent collapse of the entire glacier. Rather, it signals that one of the glacier's primary stabilizing features is becoming progressively less effective at slowing the inland flow of ice. This distinction has become increasingly important as public interest has grown. Popular headlines often compress decades of scientific complexity into dramatic predictions of sudden catastrophe. The peer-reviewed literature published during 2026 paints a far more nuanced picture. None of the major studies concludes that Thwaites Glacier will collapse within months. None predicts an abrupt worldwide rise of several meters in sea level over the immediate future. Instead, researchers consistently describe a glacier undergoing long-term change, one whose contribution to global sea level rise is expected to unfold across decades and centuries. The greatest surprises waiting inside Thwaites Glacier are not found on its windswept surface, but within the ancient landscape concealed beneath nearly 2.5 miles, or approximately 4 kilometers, of ice. For decades, that hidden world remained one of the largest unanswered questions in Antarctic science. Researchers could observe the glacier from satellites, measure its movement across the continent, and monitor the retreat of its grounding line, yet they knew remarkably little about the foundation supporting one of the largest glaciers on Earth. Many numerical models necessarily simplified the terrain below the ice, assuming a relatively smooth bedrock surface interrupted only by modest variations in elevation. That assumption helped scientists make projections, but everyone understood that reality was almost certainly far more complicated. During 2026, one of the most significant discoveries transformed that picture. Publishing their findings in Communications Earth and Environment, researchers completed one of the most detailed seismic surveys ever conducted across Thwaites Glacier. By sending controlled seismic waves through the ice and analyzing the returning signals, the team reconstructed the buried landscape with extraordinary precision across more than 211 miles, or approximately 340 kilometers of survey lines. Instead of revealing a simple foundation, the glacier rested upon an intricate geological maze shaped over millions of years. Towering ridges of resistant bedrock emerged from the data, like submerged mountain ranges frozen in time. Between them lay deep basins filled with soft sediments deposited long before Antarctica became the icy continent known today. Even more remarkable was evidence of ancient wetlands buried beneath the glacier, preserving traces of landscapes that existed during a dramatically different chapter of Earth's history. Each of those discoveries carried profound implications. Hard bedrock behaves almost like the rough tread on a tire. As the glacier moves across these resistant ridges, friction increases, slowing the flow of ice and creating localized zones of stability. Soft sediments behave very differently. Saturated with water and easily deformed under tremendous pressure, they provide a far more slippery foundation, allowing sections of the glacier to slide with much less resistance. Rather than responding uniformly to changing ocean conditions, different portions of Thwaites may accelerate or slow depending upon the geological character hidden beneath them. That realization represents far more than an interesting geological detail. For years, uncertainty surrounding the glacier's foundation limited scientists' confidence in projecting future sea level rise. Small differences in the nature of the bed could produce substantially different outcomes over many decades. By mapping these buried features in unprecedented detail, researchers have supplied the next generation of ice sheet models with information that was previously unavailable. Future simulations will increasingly incorporate realistic geology rather than idealized assumptions, narrowing the range of uncertainty surrounding the glacier's evolution. The discoveries also reveal that Antarctica has not always been an unbroken kingdom of ice. Long before continental-scale glaciers dominated the landscape, rivers flowed across portions of West Antarctica, wetlands collected organic material, and sediments accumulated within broad valleys. As climates cooled over millions of years, advancing ice gradually buried these ancient environments beneath immense layers of snow that eventually compressed into glacial ice. Today, those forgotten landscapes influence the movement of ice above them, despite having remained hidden for countless generations. While geologists were uncovering the glacier's concealed foundation, another group of researchers searched even farther into the past. Their work, published during 2026 in the Proceedings of the National Academy of Sciences, examined geological evidence preserved beneath the seafloor in front of both Thwaites Glacier and neighboring Pine Island Glacier. Layer after layer of marine sediments recorded the advance and retreat of Antarctic ice following the end of the last ice age. preserving a remarkably detailed history of how these glaciers responded to natural climate changes throughout the Holocene. The record contained a powerful message. Thwaites had not retreated inland only once. It had done so repeatedly. At several points during the Holocene, retreat accelerated rapidly after critical thresholds were crossed. Once those thresholds had been exceeded, the glacier continued withdrawing inland even without dramatic additional changes in external conditions. This pattern provides compelling geological evidence supporting a process that glaciologists have long described through theory and computer simulations: marine ice sheet instability. The concept is both elegant and unsettling. Imagine balancing a ball at the crest of a gentle slope. A slight push may produce only limited movement while the ball remains near the top. Once it rolls beyond a certain point, gravity itself becomes the dominant force, allowing the motion to continue even after the initial push has ended. Marine ice sheet instability operates through a comparable principle. As grounding lines retreat into deeper basins, the geometry of the glacier begins favoring continued retreat because progressively thicker ice becomes exposed to the ocean. The glacier's own configuration starts amplifying change. The geological evidence recovered from the seafloor demonstrates that such behavior is not merely theoretical. It has occurred before. That finding does not imply that history will repeat itself at exactly the same pace under modern conditions. Today's climate, ocean circulation, and atmospheric composition differ from those of earlier warm periods. Nevertheless, Earth's geological archive confirms that glaciers occupying similar settings have undergone episodes of substantial inland retreat once critical thresholds were crossed. Another important contribution arrived during 2026. Although researchers emphasize that its conclusions remain under scientific review. A comprehensive reconstruction of Thwaites Glacier's 20th century evolution, released as an e-geosphere preprint, used advanced numerical ice sheet modeling to retrace changes beginning in the early 1900s. The simulation suggests that for thousands of years beforehand, the glacier remained comparatively stable. Around the 1940s, however, the western portion of its floating ice shelf may have lost an important pinning point, where the shelf had been anchored against an underwater rise. Pinning points function much like natural anchors. By pressing against islands or elevated sections of the seabed, floating ice shelves gain additional resistance that slows the glacier flowing behind them. Losing one of these anchors reduces that resistance, allowing ice to move more freely toward the ocean. According to the reconstruction, the disappearance of that single stabilizing feature may have initiated a chain of changes that continues today, with ongoing ocean warming reinforcing the retreat over subsequent decades. Because this study has not yet completed peer review, scientists appropriately treat its conclusions with caution. Even so, the proposed sequence aligns remarkably well with many observations emerging from independent satellite measurements, oceanographic studies, and geological evidence. Future peer-reviewed work will determine whether this reconstruction becomes part of the accepted scientific understanding of Thwaites' modern history. Perhaps the most ambitious effort to understand the glacier has taken place not from orbit or through computer simulations, but directly beneath the ice itself. During the Antarctic field season spanning 2025 and 2026, researchers successfully drilled through nearly 3,300 feet, or approximately 1 kilometer, of solid ice to reach the hidden ocean beneath Thwaites Glacier. Achieving that feat required transporting specialized drilling equipment across one of the harshest environments on Earth, melting a narrow borehole through the ice using hot water, and lowering scientific instruments into a cavity that had remained isolated from direct human observation for countless centuries. Technical difficulties prevented the installation of some long-term monitoring equipment originally planned for the expedition. Even so, the mission achieved one of its principal scientific goals. Researchers obtained valuable oceanographic measurements directly from the cavity beneath the glacier. Temperature, salinity, water circulation, and other observations collected during the expedition will improve scientists' understanding of the interaction between relatively warm ocean water and the glacier's underside. Those measurements are expected to support future peer-reviewed studies, while helping refine increasingly sophisticated numerical models describing Antarctic ice sheet behavior. direct observations remain indispensable because even the most advanced simulations depend upon accurate information describing the real world. Every new measurement collected beneath Thwaites reduces uncertainty and strengthens scientists' ability to distinguish between competing explanations for the glacier's ongoing evolution. Taken together, the discoveries emerging throughout 2026 reveal a striking convergence of evidence. Satellite observations document continued thinning, grounding line retreat, and accelerating ice flow. Oceanographic studies identify persistent intrusion of warm circumpolar deep water beneath floating ice shelves. Field expeditions provide direct measurements from previously inaccessible cavities beneath the glacier. Seismic surveys expose an unexpectedly complex geological foundation capable of either slowing or accelerating retreat depending upon local conditions. Geological records demonstrate that comparable inland retreat occurred repeatedly during earlier warm intervals following the last ice age. Advanced numerical simulations increasingly reproduce the changes now being measured across the glacier. Each line of evidence originates from a different scientific discipline. Glaciology, geology, oceanography, geophysics, satellite remote sensing, and numerical modeling all approach the glacier from unique perspectives. Yet rather than contradicting one another, their conclusions increasingly reinforce the same overarching picture. Thwaites Glacier continues to retreat. Equally important is what these studies do not conclude. They do not support claims that the glacier will collapse within months. They do not predict an abrupt rise of several meters of global sea level in the immediate future. They do not describe an unavoidable worldwide catastrophe arriving overnight. Instead, the emerging scientific consensus portrays a glacier responding to persistent ocean warming and complex internal dynamics over extended periods. Additional weakening of its remaining eastern floating ice shelf would likely reduce the buttressing that presently slows inland ice, increasing the rate of ice discharge into the ocean. That acceleration, however, would unfold across years, decades, and potentially centuries rather than in a single dramatic event. That longer timescale does not diminish the glacier's importance. Quite the opposite. Changes measured over generations have the power to reshape coastlines, alter ecosystems, challenge infrastructure, and influence the lives of hundreds of millions of people living near the sea. The significance of Thwaites lies in its enormous size, its vulnerable position within West Antarctica, and the growing confidence scientists now have in understanding the physical processes driving its evolution. Each expedition to this remote corner of the planet replaces speculation with evidence. Each satellite pass records another chapter in the glacier's transformation. Each seismic echo, sediment core, and ocean measurement sharpens humanity's view of one of Earth's most consequential natural systems. The frozen frontier at the bottom of the world remains as awe-inspiring as ever, but it is no longer silent. Through years of painstaking research, Thwaites Glacier has begun revealing its secrets, and those revelations are reshaping our understanding not only of Antarctica's future, but of the changing relationship between ice, ocean, and a warming planet.